Hello everybody, we're still talking about the convection mass transfer between phases, and we discussed the overall mass transfer coefficient, the relation between the overall and the individual mass transfer coefficients for linear and nonlinear equilibrium relations. And now we will talk about one last thing, which is a very, very important thing, by the way, which is representing the or calculating the resistance that we have in the two phases, or the species phases in the two phases to mass transfer. So we can write the flux equation in forms of a driving force over resistance. So if you write the equation in this form, you will see that I have in units of mole fraction, I have the individual mass transfer coefficient in liquid phase, in vapor phase, or in gas phase, and the overall in liquid phase, overall in gas phase. So we can rewrite the equation. Of course, each one of them has its driving force. We can rewrite the equation or these four equations in this form, where we have the numerator is the driving force, which is the interfacial concentration or mole fraction minus the bulk mole fraction, and whatever the terms that we have. And the denominator is 1 over the mass transfer coefficient. So this is the resistance in liquid phase, this is the resistance in gas phase, this is the overall resistance in units of liquid phase, and this is the overall resistance in units of gas phase. The same can be done for units of concentration and partial pressure. We can rewrite these equations as concentration difference divided by mass transfer coefficient, or the 1 over mass transfer coefficient. The same here for the four equations. This is a pretty important thing, because knowing these forms of the equation and describing the equations in the form of a driving force over resistance can tell us a lot about the relation between the individual and the overall mass transfer coefficient. So we can describe the mass transfer between the bulk of gas and bulk of liquid phases as an electric circuit, and this is something we did in heat transfer before. To transfer or to describe the mass transfer process as an electric circuit, where we have the resistance in the liquid phase and the resistance in the gas phase as two resistances in series. So the overall resistance is the summation of these two resistances. So this is what we will do here. So for the resistance in the liquid phase, it's 1 over KL. For the gas phase, it's 1 over HKG. And of course, this is using the units of liquid phase. So this is all based on the driving force in the unit of concentration. So this is how we describe the resistances. So the overall resistance is 1 over KL. Resistance in the liquid phase 1 over the lowercase kl, and the resistance in the gas phase 1 over HKG. So we can write the equation in this form. And then we can tell how much resistance is, or what is the contribution of each phase to the overall resistance. So if we want to get the percent resistance or the relative resistance in the liquid phase, it's gonna be 1 over KL divided by 1 over the uppercase KL, which is gonna be KL over the lowercase KL. And the same for the gas phase, it's gonna be KL over HKG. We can do the same based on the units of gas phase. So if I have the overall mass transfer coefficient is 1 over kg, then the gas phase resistance is 1 over kg, and the liquid is 1 over or H over KL. So we can do the same, that this is the summation of these two resistances is the overall resistance, and from this we can say that the resistance or the relative resistance in the liquid phase is HKG over KL, and for gas phase it's kg over kg. This is one important thing which tells us how important is each one of these two resistances, because this is one important parameter that we need to understand, because in many cases we are interested in enhancing the rate of mass transfer, and in this case we have to reduce the resistance as much as we can. And if you don't know this concept, then you might not know what is the phase that is contributing more to the overall resistance. So let's say I have a case where the gas phase resistance is 90% of the whole resistance. and the liquid phase is contributing only with 10% to the overall resistance. And I want to enhance the mass transfer rate or the flux, so I increase the turbulence in the liquid phase, and I increase the mass transfer coefficient in the liquid phase by any means. So what I'm doing is I'm enhancing or reducing the resistance, which is only 10% of the whole resistance. So even if I reduce it to 50%, I'm reducing the overall resistance to only 95% of the actual resistance. However, if I do the same for the gas phase, then I'm reducing the overall resistance to 60%, because I'm reducing or maybe less than, or little higher than 60%. I don't know exactly how much, but I'm reducing it a lot. So this is important. So if I know which phase is contributing more to the overall resistance, I can enhance the mass transfer coefficient in this phase and reduce the overall mass transfer coefficient. So that's why this is one very, very important thing. Now, one other thing that is very good to know and to see it visually using the graphical representation, and this is again one of the advantages of having this graphical representation, is to see this relative resistance. So we will see here two extreme cases. So here we have the general case where we have comparable values of kg and kl. So we have this line going this way. So but we have some two extreme cases, which is the first is when having slope which is equals to 0. When I have a slope equals to 0, it means that delta y over delta x equals 0. So the line is gonna be horizontal or almost horizontal. And I know the slope is negative KL over KG, and in this case, if the slope is 0, it means that KL is much smaller than KG. And this means that if in case of linear relation or in non-linear, but in linear relation the equation is going to be easier. So I'm giving this example using the linear relation. So Kg is much larger than KL, so 1 over Kg is much smaller than 1 over KL. So this term is gonna be almost 0, and in this case the overall mass transfer coefficient will be almost equal to the individual mass transfer coefficient in the liquid phase, which means that it's almost liquid phase, or the total resistance is the liquid phase resistance. So this is called liquid phase controlled mass transfer, which means that I have no resistance in the gas phase. And if you take a look at the profile to the right, this is the profile that you'll see. If you have the gas phase mass transfer coefficient is equal to infinity, it means that the flux is or the driving force is gonna be 0. You don't have any resistance to mass transfer, so you don't have any driving force. You can think of this as the driving force equals the flux divided by the mass transfer coefficient. So if mass transfer coefficient is a very big number, so the driving force is going to be 0. So anyways, it's going to be logical to think of it like this. So you'll have a linear profile in the case of gas phase, and in case of liquid phase you'll have this profile here. This is called a liquid phase controlled mass transfer. The opposite is the other extreme case, which is when we have a slope which is equal to almost infinity, which means that delta y over delta x is infinity, which means that the line is vertical. And in this case, KL over KG is infinity, which means that KL is much larger than KG. And in this case you can do the same, and you will see that in this case KL is much larger, which means that this term is gonna be almost equal to 0. So we'll have KG equals KG, and this means that it's the totally opposite case. You'll have it as a liquid phase controlled a gas phase controlled mass transfer process. You will have the profile in the gas phase that we have here, but in the liquid phase it's a linear profile. We don't have any driving force. So these are two extreme cases, and of course if you have a case which is closer to this, it means that it is, if I have a slope that is closer to being vertical, then it means that it has more gas phase resistance than liquid phase resistance. And if you have a line that is all close to being horizontal, then you have more liquid phase resistance than gas phase resistance. So this is one nice thing to know. There is one last thing that I want to discuss regarding the theoretical background of these concepts that we're discussing. It's not in the textbook, but I think it's important for you to understand and to keep in mind, because this is going to be helpful for those who are going to study any mass transfer processes later, which is the graphical representation in general. We do this for a simple process of absorption or stripping, where we have just a single point. We have mass transfer taking place between 2 points, and you saw that, or you'll see later when we do or solve some problems, that these problems can be solved numerically and graphically, and the numerical solution is not difficult. It might be like little time consuming, but it's doable. But the main advantage of graphical solution appears in processes that include more than one stage. So this is what we have in case of distillation. This is what we have in case of absorption columns. So it's not just an absorption tank or something, it's an absorption column. We have two streams going in counter current. In a tray column or in packed column, you have many stages, and each stage is contributing to mass transfer in a way or another. So in this case, let's say you have like 10 stages, 15 stages, 20 stages. You have to do these calculations for each one of the stages, and each one of the stages produces the output of this stage is used in the next stage. So the error, if there is an error in one stage, is going to be building up over the rest of the stages. So the calculations are very, very complicated, and that's why the graphical solution here is, this is what we have in distillation, this is what we have in absorption. It's very, very simple. You just put some points, draw some lines, and then draw the stages within a minute or two, you're done. And compared to the actual calculations, this is very, very, very time saving. I don't want you to think about these details, because these are dependent on the equations that describe the columns, and it depends on your understanding of the column and the assumptions on which the equations are based on. But the point I want to make is that we use these graphical solutions a lot, and that there are common things in this in all the graphical solutions, and this is what I want to highlight here. We have here the red line here, which is the equilibrium curve. In case of distillation, it's the XY diagram, but in case of absorption, it is the mole ratios X and Y. It's always also a red line here. So we must have an equilibrium curve. Here we have this blue line here and this blue line here. There are two operating lines which represent the mass balance or the mole balance. And the same here, you have this line here, which is a straight line, which represents the mole balance. And the way we put the equations or put the lines this way depend again on the equation. So this requires a lot of work to understand how things work. But the point I want to make is that this is the basic idea, is to have equilibrium curve, to have an operating line, and then draw some stages or do something to represent the number of stages that you have to get the concentration at each stage, and do all these calculations. So this is like a very important point to keep in mind, that this you might think that what we're doing is not worth all this waste of time, but in cases like this, it's very, very worthy. So you have to understand this point. Starting next video, we'll start solving some examples, try to apply what we were discussing, and we will see how we can do the graphical solution, the actual solution, or the numerical solution, and how we can apply it on different cases. So I'll see you then, inshallah. Goodbye.